So today we are in the second webinar of our 3-webinar series on e-commerce and real-time personalization. What we're going to be doing today is broken down into 3 parts or 4 parts. We'll start off with an introduction or sort of outlining the landscape of next generation e-commerce. What are the factors that are causing e-commerce across various verticals to go through a radical change? What exactly that particular change is, what use cases are emerging out of those particular changes, and then we will move on to talking about why these changes are actually to a large extent incompatible with current architectures, why current architectures of enterprise systems that are used to build e-commerce systems are not necessarily designed to address these next generation use cases. We'll then present another architecture, an alternative architecture, which is a more modern architecture, using which one can actually address these problems. We'll talk a little bit about the X platform after that. X platform is very much aligned with that architecture that we'll be describing. And then we will go into a specific use case, which is the value-based pricing use case for hospitality and entertainment. We'll do a demo around that, and then we'll move on to taking questions. So let's dive into it right away. So what is this new e-commerce? There are 3 primary factors that actually are driving these new and improved and changed use cases around the e-commerce landscape. The first is, of course, personalization. Personalization is all about knowing your customer and to drive loyalty. Of course, loyalty has become a lot more important now than it ever has been before, primarily because of the much higher velocity of information that people have at their disposal, and therefore keeping your customer engaged and knowing your customer has become a lot more important than before. But personalization actually is one step even beyond just knowing your customer. It is knowing your customer in a way that addresses that customer in real time. And that actually goes into the second part of the new e-commerce landscape, which is mobility. Now, e-commerce nowadays and e-commerce in the future is going to be largely driven by mobile. And I don't necessarily mean the mobile phone or the mobile form factor per se. What I actually mean is that the way people engage with retail, with aspects of discovery during shopping, performing transactions, trying to actually find whatever is relevant to them is happening a lot more on the move. And when such activities happen on the move, it changes the way people engage with these e-commerce systems. It's no more that the e-commerce systems can provide mechanisms by which people can discover what they're looking for, but rather it actually needs to incorporate a certain amount of intelligence to start curating and knowing based on the knowledge of the customer, so that a curated and relevant subset of the products and offerings out there are presented to the customer and presented in a way that is relevant to the customer and personalized with respect to price, with respect to their propensities, et cetera, et cetera. So between personalization and mobility, the entire mechanism by which people engage with the e-commerce systems is going through a radical change. And it results in sort of the third big sort of change that's happening in e-commerce, in the sense that because people are mobile and while they interact with the systems, because the amount of data that you have to work with in order to keep engaged with your customers is constantly changing, the velocity of information is constantly increasing, the processing of data has to actually be in motion. You cannot allow the data to go to rest because it takes too much time in order to start pulling out all the insights from the data while it is at rest. And that blows through the SLAs that you have to engage effectively with your customer. And so therefore, the new e-commerce systems have to be highly adaptive. They have to adapt to data as data moves around, and they have to constantly be able to absorb new use cases, new data patterns, etc., that they use in order to serve their customer. So what is coming out of these three? Between personalization, knowing your customer, gathering all the information about that customer, using that information in order to serve the customer who's mobile, constantly being able to adapt to newer information that's out there and incorporate into your decision making. What are the various use cases that actually are in the next generation e-commerce systems, and how they're different from what they are today? The first one is curated discovery and search. As I mentioned just a little while ago, this process of discovery cannot be anymore one in which the customer is going and looking for information based on attributes. The next generation of consumers, the Gen Z, etc., are not interested in actually performing discovery as we do today. What the view that they have of the world and the view of e-commerce systems and the systems that actually serve them is one where they believe that those systems actually should know them very well already. And therefore, there is no need to go ahead and search for stuff that they need. They expect that the information about themselves is available to the systems and to the companies serving them. And the information is curated in a way that only what is presented to them is relevant, is already been vetted as being relevant to them before it's presented to them. So curated discovery and search is a big one. The other one are real-time offers. This ties directly into the mobility aspect of the next generation e-commerce landscape, where information is moving so quickly that it is really important to be able to get the offers targeted correctly, and therefore the use of information in real time in order to target people with offers. Dynamic and competitive pricing and value-based pricing are the next, which are basically substantial improvements to the pricing mechanisms. Pricing currently happens based on catalogs being created based on certain algorithms that run in the middle office using batch systems in order to create or produce the prices that the transactional systems serve. But the information that is moving fast enough that the pricing has to be a lot more dynamic based on the market in the moment, as well as not only incorporate demand patterns in deciding price, but also take into account the value of the customer itself in order to provide a price that is personalized, that is value added, and that one that drives loyalty and actually generates much, much higher revenue. We'll be talking about value-based pricing use case today, where I'll illustrate in more detail what that actual use case is and what actually its benefits are. The others are conversational commerce, single view inventory, smart fulfillment. There are so many different use cases that are coming out. But the central theme in all these use cases, which are emerging from the theme of personalization, the theme of mobile consumption, and the theme of being highly adaptive to the data that is constantly changing, is intelligence. Essentially, what is happening with e-commerce systems and what is happening with other systems is effectively now, if the past couple of decades has been about automating enterprise systems and then making the enterprise systems more efficient through the process of analytics, using which we get insights into the systems and make them more efficient in terms of their operation as well as the business processes. The next decade is going to be about taking that insight and not feeding it to humans to feed it back into the systems, but actually automatically feeding it back into the transactional backbones that use that information in real time to make automated decisions for the consumer. It is that intelligence that actually is really the crux of the next generation e-commerce landscape and the next generation computing landscape across many, many domains. So what really is real-time intelligence? Real-time intelligence is nothing but the ability to be able to make automated decisions that is relevant to the customer. And what is implicit in any kind of intelligence is the fact that it needs to actually work with large amounts of data in real time. That's what changes the game. That is what makes the architectures that exist today not necessarily robust enough to be able to handle these new use cases. Because when you're talking about real-time intelligence, you're talking about working with lots and lots of data in the moment, and the ability to be able to pull that data, to be able to present that data to the business logic in a way that's native to the business logic and execute to it becomes really important, which the current architecture starts showing some deficiencies on. So what exactly are those deficiencies in the current architecture? So if you look at this particular slide, you will see that this is kind of the canonical architecture that exists in most e-commerce systems and actually most enterprise systems per se. You have data sources, which basically serve as the ecosystem to your enterprise, or within your enterprise to certain systems. Like, for example, let's consider this to be a transactional system. Your data sources are sources of information that are needed by the transactional systems. And there are two other layers. There is the data layer, and then there's a function layer. The data layer is basically the storage repository for all the data that's coming out of these data sources. And the function layer is the one that actually executes business function and serves the consumer, for example, performing pricing or deciding on offer priorities and so on and so forth, using the data that is stored in the repository. It's a pretty common architecture and that is used. And this data repository could be anything. It could be your RDBMS, it could be a data grid, it could be an in-memory data grid, it could be any kind of data management technologies that actually fit within this kind of multi-tiered architectural model. The problem with this particular system, this particular architecture, is that beyond a certain point, the data itself does not scale. And now, what I mean by this is not that the technology that backs these data stores is not designed to scale or doesn't have facilities to scale. They do. They have extensive facilities to scale, but the problem is that data itself has no meaning unless it actually is attached to a certain function. The way the data is scaled, the way the data is stored, the way the data is indexed, the way the data is actually updated is always optimized based on the function at play. And if you land up having the same piece of data shared by lots of different functions, you land up having a choke point where that particular data cannot satisfy the non-functional SLAs of all those different functions. That is the crux of the issue when it comes to shared data stores. And in today's landscape, where intelligence is being incorporated into the function layer, this intelligence actually is not only requiring a lot more data in order to execute the function, but also in an intelligent enterprise, you need to be highly agile. And in that agile enterprise, you actually have a lot of different functions actually using the same data to perform different functions using that data, slightly different functions. And in doing so, the data starts becoming a choke point. The second is that this model of request for a particular transaction, and the transaction at that point in time goes and queries for the data in order to serve that function, does not perform. It can perform in today's world, or like before today's world, when actually the amount of data that needed to be fetched was small. For example, when you're doing pricing, you actually can fetch just the catalog information. If just fetching the catalog or some aspect of the catalog in order to serve a particular price, yes, you can store that catalog in a data store, you can fetch that catalog on demand, and you can actually serve from that particular catalog. But what if you have to take that catalog and you have to munch that with customer value, and you have to add on top of that an intangible offer value, and you have to add into that kind of looking through the transaction history of the customer in order to understand risk, et cetera, et cetera, et cetera, the amount of data that you have to pull and the chatter that exists between the function and the data layer starts exceeding a certain point and causes severe performance problems. The third is that when you have so much of data to fetch and you have so much of hand stitching to be done between the function and the data that you're actually pulling in, and the transformation of that particular data between the native storage that actually exists on the data sources and the way you actually need it in order to execute your function, say in Java, it becomes more and more complex to author these systems. And in doing so, what happens is that these systems not only start becoming performance bottlenecks that don't perform beyond a point, they don't necessarily scale in a way that the business needs to scale, because you need to scale the data and the function layer actually in harmony, which is very hard to do because of governance issues. And therefore, the systems start becoming more brittle and start serving as more, start exhibiting more choke points than they ever did before. What is the solution to this? The solution in a nutshell is that in any of these transactional systems, data is actually coming from these data sources. And that particular data, if you recognize the fact that that data actually has meaning and needs to be optimized based on the function that is actually using it, the first thing to do is actually not store that data right away in some kind of common data storage without being aware of the function that's using it. Now, in many cases, people will tell me that yes, they always are aware of the function they're using and they're constantly tuning the data. But there are governance issues in doing that, particularly when that data is shared across domains. However, if you actually don't store it right away and you incorporate some kind of intelligent data routing layer, and that data routing layer not only performs intelligent routing between data source and function, but also can perform certain amount of aggregation and transformations, you land up actually having a very powerful system where your data is constantly on the move between the data sources, being aggregated, being transformed, and being prepared on the move for the function that actually is going to be using it. And it is stored private to that particular function, co-located with that particular function, potentially in the same memory process memory space with the function, so that the function actually has a private copy of that data in a form that is native to it and local, so it can use it and govern it in a way that's independent of the other functions. This overall makes the system a lot more agile. It allows for the system to breathe better, and it actually allows for the system to scale in a more homogeneous fashion and perform way, way better because your data is co-located with your function in the first place. So what is the X platform? Now that I've kind of introduced this new kind of architectural pattern, the X platform is a platform that for all practical purposes is designed to actually solve this particular problem we just talked about. And it enables the architecture that we just discussed. In a nutshell, the X platform is a platform that was built with one simple goal. The goal was to be able to allow enterprise transactional systems to be built very easily, with the developer taking care of only the business function while the platform takes care of all the non-functional concerns. Architecturally, it uses in-memory computing techniques plus multi-agent computing in order to enable the architecture that we just talked about. We call that architecture actually capture, aggregate, transform, and store architecture, and as opposed to capture, store, query, aggregate, and transform, which is kind of the opposite of this particular architecture. There are 4 key tenets to any platform that needs to address this architecture, and these 4 are addressed by the X platform. The ability to be able to perform data capture through sophisticated gateways that can connect into other systems, that can connect into databases, that can connect into CSV files, that can connect into external messaging backbones in order to draw data down and capture that particular data. The ability to be able to route data, and while routing it, to be able to perform transformations as well as aggregation of information. The ability to be able to visualize data, which is a really important part of these kind of frameworks. And finally, not only to be able to just move this data around, but also to present it and store it in a way that's co-located with the function to perform intelligent transaction processing. The 2 core tenets of the X platform, as I mentioned, are the X platform is in memory, which lends to high speed and extreme simplicity. In-memory computing actually does lend itself to a deep amount of simplicity. as well as multi-agency, which has several benefits. And those benefits are actually reflected in the architecture pattern that I just discussed, which is effectively a manifestation of multi-agent systems. So if I have to summarize what the X platform is, an X platform effectively enables an architecture or systems where you have multiple agents collaborating with each other using message passing. Each agent is actually private state. That private state is held in Java, that is private, that particular agent. The X platform makes the data management and state storage very, very simple by taking care of all the non-functional concerns around state management. And the state is completely durable over time, not transient. It is durable over long periods of time, as well as making messaging between these particular agents extraordinarily simple by incorporating the notion of fire and forget. By actually making data management simple through providing the illusion of memory being durable and make messaging very simple and incorporating sophisticated routing, it provides the foundational framework in order to actually enable architectures such as what we just talked about. And that architecture is manifested using the X platform in such a fashion. All three layers, the data sources layer, the routing layer, as well as the processing layer in that architecture are enabled through X platform agents. In the gateway layer, these agents effectively are bridging external systems to an internal system. In the routing layer, they're effectively infrastructure micro apps. We call these each agents micro apps. They're infrastructure micro apps that do things like aggregation, transformation, but keeping data on the move. And there are the processor micro apps, which actually implement business functionality, which serve as the other edge of such architectural framework. Why X platform? Because X platform has actually got one key innovation, which is the AEP engine, which does the job of stitching together data, function, messaging in your micro app in order to actually make make it very easy to write micro apps and basically hook micro apps together using messaging. And if you have that capability of being able to write agents very easily and to be able to stitch them together through and connect them together through very easy messaging, you actually have a very powerful backbone at your disposal using which you can create very, very powerful hyper-distributed systems such as the architecture that we just talked about. Using X platform, we claim that it'll save 60% in time, money, and opportunity because it actually takes away all the burden of non-functional concern from the developer. The developer only focuses on business function, and it is extraordinarily fast by virtue of in-memory computing, as well as completely available, I mean, totally reliable, as well as scaling linearly. I'm going to skip the next 3 slides. These 3 slides are actually there for folks who actually want to browse through this deck at their own leisure. There's some detail here from a technical standpoint for people to understand the architecture of a micro app internally, a few more, the modules that actually make up the X platform, as well as sort of what are the development artifacts that you need in order to build these particular agents. I'm going to skip these. They're available on the deck for your perusal at your own leisure. Let's move on to value-based pricing, the use case. Value-based pricing, let me explain what it is first. The use case that we're talking about today is value-based pricing in entertainment and hospitality. In entertainment, specifically gaming, like in Vegas and the resorts and the gaming companies. Now, in such companies where you have a combination of gaming and hospitality, or for example, like Disney, where you have a combination of theme parks and hospitality, where there is kind of an add-on to hospitality or a combination of hospitality and something else, there is an opportunity to be able to leverage the value of a customer based on the spend in certain areas of the business, such as on the theme parks or on gaming, in order to influence the prices they get in the room. Basically, incentivize customers to come and stay by giving them discounts in exchange for a higher return, say on the gaming floor or on the theme parks. Now, traditionally, the way pricing is done in hospitality is based on forecasted demand. There are systems like revenue management systems that actually look at a demand calendar. They combine the demand calendar with past reservations, reservation history, the current inventory, And they're constantly spitting out new rates. And these new rates are effectively designed to maximize the yield on the rooms that are being sold. And the yield is being maximized based on forecast and projected demand. So that's pretty much the way a lot of the pricing happens for hospitality as well as for airlines and other industries. Now, what it's not taking into account when it's doing pricing like this in verticals such as hospitality plus gaming is that it's not taking into account the value-based pricing, which is the value of the customer, and in many cases, the value of the offer that somebody is trying to redeem. So I'll give you an example where somebody lands up in Vegas or somebody lands up in any of the casino towns. And let's say there's a fight night. And when there is a fight night, somebody is actually, let's say I'm really interested in fight nights. Now, because it's a fight night, it's a high demand night. And because it's a high demand night, the prices that are put out by these revenue management systems will actually be very high. Just like if anybody had seen CES prices in Vegas recently, they were very, very high because of high demand. Now, assume that I, as a customer, on an average, basically spend, say, $1,000 on the gaming floor when I actually come to Vegas. And let's say that because of high demand, the room was priced at $700. Now, if I see $700, I'm not going to come to Vegas. It's too high. So therefore, it is by virtue of not applying the knowledge that I have a gaming propensity and I actually will be, the company overall be making money if I went onto the gaming floor, they effectively are losing some revenue. What value-based pricing does is it takes the traditional pricing model and overlays on top of it average spend of the customer or propensities of the customer and gives a price that factors in a value of the customer that actually could be recovered in a different area of the enterprise. Now, if you take this demand-based pricing system and you actually try, you take this the demand-based pricing system and you apply it to the older architecture that I talked about, it works just fine. And the reason why it works just fine is there is data capture that happens from RMSs, the data which is your pricing data, the rates to the rooms, they are stored in some kind of storage. And when you actually, a transactional request comes in for a price, you go to the storage, you fetch the catalog that has the price, and you serve the price. The reason it works just fine is because you have a small amount of data that represents that entire pricing catalog. Let's say you have 500 rooms and you have a booking window of, say, 200 days or even 400 days. You're talking about maybe about 20,000 or 200,000, I'm not sure exactly, but a small number of prices that you need to store. You can fetch that 20,000 or 200,000 prices from the data store in a matter of like, single double-digit milliseconds very easily. And therefore, you can actually use this architecture in order to solve that particular problem. The problem, though, happens when you actually now do value-based pricing using this architecture. The reason why it falls apart is because now, suppose I use the same model when I need to create a catalog of prices that are used by the pricing API or the pricing function. You're now talking about not only just the number of rooms multiplied by the booking window. Each customer has its own price, and each customer offer combination has its own price. So you will end up having a huge multiplicative factor that becomes prohibitively expensive to store. So you can't use that catalog model anymore, and therefore you can't actually store this data anymore. What you actually need to do is potentially actually compute. You need to compute this particular price on the fly. And the problem is, if you try to do that by storing the raw data in the data grid, the amount of data that you have to fetch from the data grid will goes up too much. And you land up actually that once again serves as a choke point. Not only does it go up too much, that in these environments where you're doing value-based pricing, there are constantly new factors that are actually being fed into the algorithm in order to improve the value. Every time you add one more, there's one more fetch that happens to the data store, and your system continuously starts degrading. And so you need a different mechanism by which you solve this problem. You solve it using the CATS architecture that I talked about. What you do is that you put an aggregate or a routing backbone in between, get rid of your centralized data store, and you actually push the rates from your RMS, from your offers and those spend events, which are your customer spend events. You push them raw through the system, aggregate it and transform it along the way, and store it along with the pricing service in a form that is usable by the service. So rates may be in its raw form, offers a little bit massage with some information in it, spend may be aggregated in order to give me spend by classification or spend by season, etc., that I can use in my algorithm in order to actually serve the customer. This particular architecture scales because you're actually constantly working with data on the move before it's getting to rest. And by the time the data gets to rest with the function, it's already in a form that the function can use very easily and hopefully in memory locally that is even easier and faster to access. This is the architecture that the X platform actually promotes. This is the way X platform would solve this particular problem. And that's what we're going to be demoing right now in order to showcase how this particular system, works. So this slide actually talks about the actual demo. What are the pieces of the particular demo? So the way the demo has been built out is, as I mentioned in the previous slide, you need the capability of being able to push in, say, customer spend events. Every time a spend happens, you need that information to come into the system so that actually you can calculate the aggregates. You need some mechanism by which offers, are bridged to an offer management system, or actually are coming out of a database, or you could create the value-based pricing service as a system of record for offers itself. And then you need a mechanism by which you actually bridge to the revenue management system in order to get these rates on a continuous basis into the system. The X platform gives you a gateway framework using which you can connect up to these particular systems, whether they be actual systems or databases or CSV files, or there's a whole integration mechanism by which you integrate with your existing data sources in order to source this information in real time. Even from flat files and databases, we'll use the notion of triggers and polling for the files in order to get it as real time as possible to move that information into the value-based pricing service as quick as possible. In this particular demo, the gaming gateway, the offers gateway, and the RMS gateway are actually pushing the information out through artificial events. They're generating events and pushing it out. But in a real life system, they actually would be bridging to real systems to pull this information in. This particular, so that is the gateways. Then there is the value-based pricing service, which is a sharded service that is stores all the data in memory. And the data that it stores in memory are the yielded rates from the RMS system, the offers from the offer bridge, and the aggregated customer spend, which is the customer value for all practical purposes from the gaming gateway. Now, there could be a lot more gateways out there. You could, for example, connect to a credit card payment gateway in order to get information from there, to get more information, and so on and so forth. There is a lot of information that you can just aggregate in through these gateways into the value-based pricing service that augments its algorithm. This data that is in memory is actually facilitated by easy messaging between the gateways and the pricing service, gaming spend events, offer update events, and rate update events by virtue of X making it very easy to do messaging and very easy to write these kind of app agents or micro apps. You can actually build this system very easily. The system that I'm showing you was actually built in 2 days. And so it's very simple to actually build a system like this in order to kind of draw down data and start processing that data with the data being stored in memory. The total amount of data that is stored, that is being used in this demo is 2 million customers are being stored in memory. There's 500,000 offers also being stored in memory. And the rates are being actually pushed for 500 rooms for a 2-year booking window. So 730 days of booking window with 500 rooms. That kind of determines how large the push is from the RMS gateway to the value-based pricing service in terms of updates of rates. The rate at which these gateways are pushing data down is the gaming spend events are being pushed down at 100 gaming events per second. So that's basically representing as if there are gaming events happening across these 1 million customers or 2 million customers at about 100 per second. This can go up to 1,000, 2,000, 10,000. It actually doesn't really matter. We've tested with that and it works just fine. The offer gateway, actually, it's one offer being updated every second, which is actually quite a lot for an offer management system. And the RMS gateway, where we're pushing for 500 room types and 2-year booking window, about 365,000 rates are being pushed every 30 seconds. So, a new about 365,000 rates are being pushed every second into the value-based pricing service. And the value-based pricing service is receiving all this information and at the same time serving out an API for pricing to the pricing driver, which is actually exercising the API at 5,000 pricing requests per second. All of this, the logic inside the value-based pricing service is a few hundred lines of Java code. It's pure Java. And I'm not going to show you the code right now, but hopefully you'll download the code and you can take a look at it. It's 100% pure Java. And the logic is fairly straightforward, is to get the rate that for that particular room and date, for a particular trip, in fact, find the customer, find the best price perpetual offer, and then overlay all of this and munch it together using algorithm to give you a final price. All that logic is there in the code. It's very easy to figure out, what that logic is based on the code because it's all just regular Java. There's no external footprint there. And this is basically what the system is that was built out. And I'm just going to now actually showcase the system to you as to how it actually operates, what the performance is, and some reliability concerns, etc. One thing which I did mention, which I want to repeat, is that the value-based pricing service itself is horizontally scaled by customer into 3 different shards right now. And basically, it linearly scales with customer. As you add more customers into the system, it can scale. Right now, these 3 shards are not using the amount of memory that's been given to them at all. Like 32 gigs per shard has been provided right now, but it's only using about 8 or 9 gigs, and therefore it can scale a lot more than that. So let's go straight to the demo. Actually, before I go to the demo, maybe I'll just give a quick glimpse of the code. I'm not going to go through this code in detail, but you see right in front of you are sort of an example of what the code looks like with respect to X platform applications. You see it's all pure Java, where your messages come in as Java objects. Your state, which is your repository, which you model using XML and X, actually is presented to you in X as Java. So you're effectively working with state, with messages, with business logic, all in Java, as if they're regular POJOs, and X takes care of all the non-functional concerns around it. I just wanted to point out that part of the code, which is an important part, because that lends to a tremendous amount of agility and productivity when writing X platform-based applications, which are very important when working with intelligence systems, because there is constant evolution of the logic that happens in these systems based on data patterns that are observed in production and outside. So let's move on to the demo. This is the dashboard that is used by the X platform. It's an X platform dashboard in order to manage all the X platform agents running in an environment. On the left-hand side, you will see all the micro apps or agents that are running. There are 3 pricing services partitions that are running, and each partition has a primary and a backup. The primaries are indicated by a green and backups are indicated by a blue, and they're running in a hot standby fashion. And we'll perform a failover now and actually showcase as to how robust the system is with respect to failures, etc. All of them have been launched. They're all running, all the pricing services, as well as the pricing driver, as well as all the gateways. The gateways are active right now in pushing data to the pricing service as I described before. And you can see that over here. These are rate updates sent. You see that every 30 seconds, there's a big spike of approximately 400 odd messages that are coming in. Those 400 messages are for the various room types, the 500 room types, 1 message by room type, landing up with total about 365,000 rates across all the room types that are being pushed out. So this spike is for 365,000 rates being pushed out to the pricing service. You can see over here the amount of rate updates sent and the number of updates received by each of the pricing service partitions. They're all in sync. The number of gaming events that have been sent, which is at 100 per second, as illustrated by this graph here. You can see they're being sent at 100 per second. And they're being received in a sharded fashion because it's finitized by customer. And then finally, you see the offer updates, which are 1 per second being sent out. And you see 500,000 and 340 because the 500,000 were the original amount that was seeded into the system, and then it's been updating them on a continuous basis once per second, as illustrated by this particular graph. So what you're seeing is the the value-based pricing service is running and absorbing all these events that are coming in at 100 per second from the gaming at 365,000 rates for every 30 seconds from the revenue management system, and one offer update per second from the offer management system. What I'm going to do now is I'm going to trigger a test where basically the pricing API actually requests for prices for a trip. And so we're going to be requesting for trips that are between 3 and 5 days long. We're going to do about, let's say, 2 million of these pricing requests. Or let's do actually 5 million of these pricing requests. And we'll do it at 5,000 per second. The pricing driver will actually now send out 5,000 pricing requests per second to the value-based pricing service, and the value-based pricing service will do its work and send it back to the pricing driver, and then we'll see what the response time looks like and how the system is behaving. So give it a second while it actually just spins up a little bit. So as you see, this particular graph over here is showing you the number of pricing requests sent per second. This one is showing you the number of pricing responses received per second by the pricing driver. This is the pricing response time that is you're seeing from the from the pricing driver's point of view, that it's receiving responses. You can see at a median of approximately 298 microseconds. That's the round trip round trip response time that it's taking from the pricing driver to the value-based pricing service. The value-based pricing service does its work. It's in a fully fault-tolerant fashion, and then returns back a price for each day of that particular trip, looking through all the data that it has, and returns back a price to the pricing service, a pricing driver, and you see that it is running at about 300, between 250 to 300 micros. This shows you the number of pricing requests sent, the number of pricing responses received, and of course the rest of it is as I showed you before. So what I'm going to do right now is I'm going to kill one of the partitions, and let's see what happens. So I'm going to kill the first partition. I'll just knock it over. So if you notice, when I just knocked it over, this is basically the rate at which pricing responses are coming back. This is the rate at which pricing requests went in. You'll notice over here that there is a slight blip that actually happened, and that blip was actually because of the failover. You'll notice that the pricing service has gone red, the one which I killed, and one of them, which was blue over here, actually immediately took over in a hot standby fashion, has taken over the full operation, and you see that there is no effect to the response times. It's still sitting in 300 micros range, whether it's running clustered or standalone, and there was a very small blip in the pricing responses that was caused by this particular request. So that pretty much showcases the performance, the reliability, and I'm not showcasing actually what the scalability characteristics are, but I kind of described it that it is partitioned by customer. You can add more partitions to the value-based service in order to scale it out more by customers. It is a completely in-memory system. That's the reason you're getting this kind of performance with heavy optimizations and work being done on the messaging layer in order to make this very, very performant, as you can see. So you can do 5,000 transactions a second over a 2 million customer base with 365,000 rates being updated every 30 seconds, with offers being updated every second, in kind of a couple of hundred micros, fully fault tolerant and totally resilient. I could bring up this particular service right now, and you wouldn't see this graph change. It'll join the cluster back in seamlessly. It's just that I'm not going to do it right now because we're running out of time. So with this, I will stop. Just want to make sure that I summarize that the X platform is a platform for intelligent transactional systems such as the value-based pricing system. It actually enables architectures that we believe are designed and serve these kind of applications better, especially applications that actually work with large amounts of disparate data in order to make real-time decisions and process real-time transactions. The architecture is what we call the CATS architecture, which is different from the older architecture where you store before you actually process. We believe that this architecture actually is very compelling and works for these kind of applications and other applications out there. In general, the X platform is a general purpose computing framework that is based on the multi-agent or distributed computing paradigm with in-memory kind of thrown into the mix, allowing for in-memory agents to be built to be and use message passing to talk to each other in order to build very, very compelling applications such as what we've just seen, which is the value-based pricing system. So with that, I will close and we'll open for questions.
Thank you, Girish. Let's see, we do have a couple of questions coming in. It looks like the first one is, what have you found is the most challenging task for organizations trying to do value-based pricing?
Well, in my experience, the most, I would say that it is actually figuring out what the pieces of data are that you need in order to feed it into the value-based pricing algorithm. In many cases, it turns out that the algorithm itself is easy to build, but because you can do it very simply on the X platform, but getting that data sometimes does become a challenge. And that's the reason why we have the gateway framework that allows us to be able to get that data from a variety of different places in order to source it into such a value-based pricing system. But it is mainly the identification and the sourcing of that data in real time that does pose the biggest bottleneck.
Okay, great. Let's see. I believe we have one more. What is the best practice or technique for integrating all the required systems for doing the advanced strategies like value-based pricing?
Oh, I would definitely say it's the X Platform Gateway Framework, because the X Platform Gateway Framework allows one to be able to connect to databases, to be able to connect to CSV files, to be able to connect to Kafka-like backbones, connect into output of Spark computations or Spark jobs. I mean, there are a variety of different frameworks or gateways that we have that allow you to be able to connect into systems real time, or absorb batch-based information and convert it to real time as much as possible in order to feed it to these systems. So I definitely think that the X Platform Gateway Framework is, and it's very easy to write gateways. So it definitely is the most compelling framework that I can think of.
Great. All right, if we don't have any more questions, give everybody just another moment. Doesn't look like we do. Thank you, Girish, for today. That was very informative. And remember, everyone, we will have our next e-commerce webinar on February the 8th. We will be sending out invitations very shortly. And again, the recording will be up for your viewing pretty quickly. And then we do have the slide deck and the use case available for your viewing also. Again, thank you, everyone. Thank you, Girish, and we will see you in February.
Thank you, everyone.